Okay. All right. Welcome everybody, and thank you. Welcome to another Incosi Canada chapter webinar. Our topic today is artificial intelligence and the resurrection of systems engineering. I'll first provide a little background and then I'll introduce our speakers. So autonomous vehicles are already demonstrably safer than human drivers, yet no regulator can certify this claim in the same manner that we certify elevators or autopilots. And now this is because a learned driver's behavior is demonstrated statistically, not specified in advance. The same gap opens wherever physical AI gets embodied in warehouses or factory floors in the home. The moment a robot's behavior comes from an opaque model rather than a specification. This talk presents Continuous Statistical Assurance, or CSA, a framework where the certificate itself becomes a live, machine-readable safety envelope that providers and regulators read identically in real time. This overview or background was provided by Neil, our guest speaker. So Neil Shaw is a product and systems leader working at the intersection of AI and safety critical hardware. Neil has over 15 years of experience at Jaguar Land Rover and Lucid Motors, where he's taken vehicle programs from concept to production, including the Jaguar I-Pace platform, now deployed as Waymo's autonomous fleet vehicle. He has also built early brake-by-wire and steer-by-wire systems. At Lucid, he led technical product planning for a greenfield vehicle platform over $3 billion and a 150-person organization, and shipped the company's first production AI workflow. Neil is a chartered engineer. I'm a mechanical engineer in the UK, now focused on bringing industry to physical AI and robotics. And Neil is the author of a recent publication entitled Certifying the Black Box, Continuous Statistical Assurance for Autonomous Vehicles of this year publication. And that is also the title of Neil's slide set. There'll be a Q&A session after the main presentation, and please note that this is being recorded. I now wish to welcome Neil for today's presentations. So Neil, please feel free to take over the screen. I'm going to mute, and the screen's all yours.
Thank you, Evan, and thanks, Incosi, for having me. It's a pleasure. Let me share my screen. I presume you can see me.
We can see your screen, yes.
Perfect, excellent, thank you. So similar to sort of adding to what Ivan was explaining, it is a subject that I've increasingly found gravitated to in the recent times, because I've worked in various different domains within automotive, and I've learned that generally when it comes to physical systems, we take things fairly sincerely. We'd like to make sure that it's safe before anything goes out in open road or public. With AI, the things are changing so rapidly that it is it just feels my control-seeking self does not feel comfortable. Hence, I started getting more involved, and turns out there is a lot more activity going on in regulation side as well. And few interesting things happened in June that we'll talk about as well this year. And I'm also working on a subsequent paper that goes into a little bit more detail about how this can be realized. So having said that, thanks for having me. And to start with, I'll explain what these numbers are. So 94% fewer serious injury crashes is the number that came from Waymo when they published, I think, March this year. They've finished 220 million miles, and they're showing that they have 94% less than human. serious injury crashes, and the data comes from NSTS. So it is proven, and Waymo is not the only operator, by the way. There are other operators, but at least Waymo has more disseminated log of their safety case as well as the actual miles. And what that shows is that it is quantifiably safer than average human driver, at least in US. But we cannot certify that. There is currently no body that actually certifies that. There are regulations which are different across the world. So US federal authorities generally ask for self-certification from all these providers or operators. Europe, Japan, China, I think in some sense do require some kind of certification. Europe more so, where it is third party or a regulator-led assessment. And I wanted to explain or clarify that I'm not AI doomer, or I'm not someone who believes that no, the industry must be subject to checks and measures and should be regulated. It is more to say that this not having a structure is also a problem. And I can say that from something that I experienced a few years back. So before the GDPR, the general data something regulation for Europe came over. At that time, there was a lot of fear in industry for all the operators that they did not know what's safe, what's unsafe, what's legal, what's illegal. What can they do with people's data? Now, after having the GDPR regulation, it was clear. Now people could actually operate with more speed because they knew precisely what's allowed, what's not allowed. And similarly, I think when it comes to robotics or autonomous vehicles, the problem is also that the change in technology is generally that benefits everyone, but how well someone deploys that, that's down to individual players. But how it tarnishes the industry or technology, that is usually across the board. Hence, not having a structure which sort of rewards good safety case is bad for everyone. Hence, the talk rather than stating that we should control this progress. Because I understand that industry usually is rapidly moving, and it is difficult for regulators to precisely know where what exactly within the technology is right or wrong answer, or there might not be one right answer. Hence, it's important to have some sort of structure, and hopefully this method allows that. And I also plan on, as I said, a little more clarity in terms of what could be the defaults. So having said that, let me give you some, see if it moves, some history of where we are and how we came here. So not everyone knows that the first autonomous drive across US happened in 1995. That was over 30 years back. As it It wasn't 100% autonomous. It wasn't level 4 autonomous. It was steering, and that happened, I think, 98.2% of the drive, where the human driver controlled acceleration and braking. But that was still used with neural networks. Hence, that was the first proper autonomous driving, you can say. And then things moved afterwards, kept on picking up space and speed since 2010s. Google logged 500,000 miles. They also got first driver behind the wheel approval in 2014. They got their non-driver testing approval, I think, in 2018, and 2020 October, I think they got their first commercial approval where they could actually start a taxi service. And they came to San Francisco in 2023, surprisingly in August, which is about 3 years. Like, I think end of this week or something is the 3rd year anniversary for that. And I don't know if any of you have been to Bay Area or San Francisco Bay Area recently. It is difficult to imagine that this was only 3 years back that it started, because they are everywhere. They are omnipresent, the Waymos. And having said that, things then moved not just for Waymo, but for other industries. You may know of a little-known company called Tesla. Their leader also promised full self-driving a few years back, and they have famously titled that as autopilot. They also moved from what I will explain, I think, later on, from modular to a full end-to-end model. So it is sensors and perception data in and trajectory out, or actuation out. So it is one model that, truly similar to the large language models, takes an input and gives out output. As well as now there is trend or direction towards large driving models, which is effectively your vision, language, action models or world models, where it's trained on plethora of world data from internet, from various different places, not just driving data. And that truly improves the generalization of driving capabilities, but it also makes it incredibly difficult to figure out how it derived any conclusions. So that's the status. And hence, if you notice, since 2020, when Waymo's first car was launched as a taxi, within 6 years, it feels like we made 3 different major technical changes, as well as leaps in terms of how many robotaxis we see. In San Francisco Bay Area, you would see Waymos everywhere, Zoox, as well as Nuro, and few other players around there. Waymo, when I last checked, had about 4,000 cars which are taking paid customers. So things have moved rapidly in the last few years, and they are moving rapidly. And this is, I have more knowledge of automotive or AV industry, but this is true for robotics as well. So something probably worth explaining at this point. I'm not sure if everyone's familiar with the level 0 to level 5 of full of self-driving or autonomy. So SA, Society of Automotive Engineers, came out with different levels of autonomy many years back. I remember working on it in 2013, 2012, so even before that. And what it means is level 0 is absolutely no support automation whatsoever. Level 4 is where vehicle can basically go from A to B without giving any control back to the driver. But it is still limited to whatever is the operating domain for that vehicle or model. Level 5 is there is no limitation. It acts everywhere at all times in all conditions. Most of the discussion you would hear nowadays is level 4, and Waymo is level 4. There are a few other players trying to achieve level 4. In passenger cars that you and I can buy, you would usually see systems which are level 2 capable. Sometimes some features which are level 3. So I know BMW and Mercedes have some level 3 features, but at large, it's level 2. And believe it or not, even Tesla is level 2. It's level 2 plus, but it's level 2. So how things have changed within the level 4 world is it started with modular pipeline. And this is what is the predominant structure for most of the robotaxis right now. So Waymo is modular, Zoox is modular, and few other. What it means is that there are 4 major modules within that: perception, prediction, planning, and control. So each module has, it can be a neural network, it can be multiple neural networks, but that module effectively takes an input and gives an output. Perception effectively takes the sensor inputs, whether it's camera, LiDAR, radar, wheel speed sensor, IMU, all of those, and gives an output, which is human readable and something that prediction module is trained to take as input. What that means is that between each module, there is an ability for someone to intercept and see what's the output. If there is a problem, you can go back and diagnose that this is where the problem is. And at least you know at every step what's going on. So things never get completely opaque or completely black. Since then, things have moved more towards end-to-end network, where, as I mentioned, Tesla have now moved on to end-to-end, where it is literally just one model. It takes in whatever perception or sensor inputs are, and then gives out actuation to wheels and steering and brakes. What that means is that there is no ability to intercept these modules and figure out if there is a problem somewhere. And it also changes as it updates. So OTA updates would actually change the model, what it does, and effectively what went out of factory on day 1 is not the same in 6 months' time after 2 OTA updates. So it's pretty important to understand that as a problem, because so far, for over 100 years, I think UL started 100 and something years back, I think late 19th century. Since then, we've always had ability to test systems, specify that this is what the system is supposed to do, these are the boundaries, and someone is now willing to sign on the dotted line saying that, yes, this is safe, okay for sale, or okay for deployment. That's no longer the case here. And not just that, it's also difficult to figure out how to measure whether it's good or not. Hence, in US, self-certification is the only option currently. Europe and few other countries have put in some preliminary interest and structure, but no one has managed to actually get certification done. Hence, this is still a hot debate. And the next step, which is already in play, is large driving models. So the difference between end-to-end model and large driving models is end-to-end models are still trained on driving data. Large driving models are effectively similar to your large language model, where it takes in data from the world, from the web, from various different sources, and the aim is that it generalizes the knowledge. So it can predict, or it can act in situations that it hasn't seen before. I think I saw years back there was a video that Wave, the British company, came out with, where the car is driving through London. There was a newspaper on the road, and the car just drove over it, rather than braking and figuring out what to do with this unknown thing. Because we don't expect newspapers on the road. And it was explained in that video as well, or later on, that it was not part of any training data. Hence, the car knew what to do. And that's the next step, which is large driving models. And it can take different forms. Some may call it vision language models. Some may call it world models, but effectively it is general consideration is that it's 10 billion parameters and more of a model, which is capable of reasoning. And that effectively means that you haven't really trained it on specific use cases. You haven't gone and tried that, okay, what happens in this specific scenario? It is large by nature, and it is supposed to take everything in. What that means in summary is that it is improving the capability as we move from modular system to large driving model. But it also at the same time becomes more and more opaque and less certifiable from traditional tools. So going more into detail, trying to explain what Waymo's data is currently. I think in May last year, May 2025, they had 56 million miles. Now they have 220 million miles, as came out in March, I think, this year. Their safety data compared to human benchmark shows that police reported crashes were 57% less, injury crashes were 85 or 82% less, serious injury or worse were 91 to 94% less compared to human drivers. And it's also worth noting that not all of these small incidents are reported. There is also some data, some research that shows that not all data that is reported to police is all that we have for incidents. Hence, the actual human incidents are a lot more when it comes to not serious injury crashes or incidents. Hence, reiterating my point that it is not because I feel that this is unsafe, it is to say that this is safe, but there should be reward for safer operators who take the whole system in account and design accordingly. And I think the systems engineering experts would agree with that. I think generally that sort of explainable structure is important. And to sort of explain more from the functional safety SOTIF FMEA point of view, traditionally functional safety expected 99% or still does expect 99% provable safety. And that is just not possible with the real world scenarios where the scenarios are innumerable. What we see as numbers are the comparison to human drivers. There is nothing that says that these are the 100% of scenarios that we can enumerate. Hence, it's not possible to come to that 99%. And there is another aspect, which is what the functional safety does not comprise of, called safety of the intended functionality. So what that means is that if the functional safety takes care of failures when something fails in the system and it does not perform as intended, what SOTIP does is that it is trying to figure out and design a system that if something goes wrong, what happens? To give you an example, if let's say there was a robo arm is tasked with screwing something on a panel in the plant. It has gone out of calibration slightly, and now it misses that by 2 millimeters and then does not actually screw that in. Nothing really fell because the panel had 12 different screws. This was one of them, so the assembly still passes the plant assembly and checks, and it goes out to public like that. So it failed. All of the aspects of the system did what they were supposed to do. The QA performed whatever test they were supposed to do, and it still passed. Robo performed whatever it was supposed to do, and it did not really fail at the actual action, but this was still a failure. And that happens in AV as well, where, to give you an example, I think Tesla had that issue where in dense rain, there was some fog buildup on camera, and then it could not reliably see the scenario in front, and it failed. So that kind of scenarios where the system performed as it was supposed to, the camera lens actually took whatever it's supposed to. It's just in front of the lens there was something, and that kind of scenario are something that needs to be taken into account, which is not something we are equipped with traditionally. So there are benefits of having the shared procedure, and I'll explain more in detail later on that how having a structure allows smaller players to perform as well. Giving some numbers, San Francisco, I think, reported, or firefighters or authorities reported 31 incidents with robotaxis. There was an incident where a fire engine effectively was held by a confused Waymo, I think, for 15 minutes when it could not figure out, because the situation was not something that it encountered or it had learned. We humanly normally just do what seems like common sense, that, oh, there is an authority, we are supposed to move out. That's not how computers work, as we know. So either we have to specifically program that, or we have to allow them to generalize that knowledge. And these kind of incidents have happened all over, not just in California, in Texas and a few other places where emergency services tried to respond to something, and they effectively were halted by robotaxi, and they had to intervene. There is a painful communication between the officer and someone who's in the headquarters doing the teleop to figure out how do they authorize that action, whether the officer who he says he is or she says he is actually the officer or someone else. All of that. So it's complex, and it's not something that any of us want in case of emergency. So it's important to have a shared structure, because this is the same problem that all of the players have, whether it's Waymo, Zoox, Neuro, they all have to work with the authority, have to work with emergency services. But if there is no structure, it's not easy for anyone, neither for the providers nor for government or authorities. And another frustrating part, which is probably not very related to the AV system, is they had to call, like Waymo called 911, which is the emergency service in US, over 100 times, just because the passenger was asleep and Waymo could not do anything at that time. So these kind of problems mean that having an agreed structure helps, as well as the fact that if it is a common structure, it benefits smaller, new players within the field. It does not just reward incumbents where the amount of miles are enormous. So certainly there are benefits of having more structure, and it is not to say that how do I explain without sounding like a broken record that I'm very pro certification. Something that happened this year in June, UN GTR, which is the technical regulations body within UN, they adopted in-service monitoring as one of the things that they expect from AV operators. And at the same time, NSTSA had a program called AV STEP. They withdrew that because it was rejected by both sides, whether it's operators or regulators. Operators stated that it is too cumbersome, it takes too much effort to prepare the evidence every 3 months, and all of the requirements are just too much of a burden and bureaucracy. The regulators rejected because they felt that it was based on the fact that it was voluntary and not enough structure. It wasn't comprehensive enough to actually make it more safer or add value. And hence that shows how this problem is not just hard, it's not just work to be done, it is complex. And trying a little more technically to explain what that means. It's non-compositional, so it is not something that we are used to, where traditionally as a system, we would take all the components and subsystems and put it together, and it's possible for us to say that all of this together would do this. And we have diagnostics coverage, and we have ways to test and verify that this is what it's supposed to do, and this is what it would do. That's no longer true. So it is either something that you would experience by doing it, or you figure out other ways. That's why the paper. There are two distinct problems. They're sort of famously known as curse of what are the two names? Curse of size and long tail. Effectively, how often you would encounter certain situation. So long tail problems are famously long tail, especially in the real world scenarios, where they are encountered rarely, hence expecting your normal drives to encounter that, and you being able to resolve that is unlikely. You will always have some edge cases that you would miss. And hence, if you were to go with the approach of testing empirically all of the use cases, you will fail. And alternative, the flip side of that is that the sheer scale is such that if you were to try and just accumulate miles, it is prohibitively restricted to be able to go through that many miles. To give you a little bit more clarity, many years back, there was a study that came out by Grand Institute, and they calculated that to gain 80% of competence of a human driver at 95% confidence, the system would have to demonstrate 275 million miles to statistically show that this is safe, because you cannot enumerate the real life. And that just explains how prohibitive it can be if someone wants to start operating. And because of that, if we rely on self-certification, it's unlikely that we would get a comfortable solution and confidence. The third issue being the narration, something that I would discuss more in a few minutes' time, is also not something that is easy, because the models, some of you may know, don't really say what they think. Hence, that's a problem. And then it does not hold still. Policies change, they are constantly improving. So with OT updates, it's constantly a new system that is acting, and it's not the one that left the factory. So it's important to resolve and come up with a system that takes care of these things, because the traditional approach we have does not. And It's not to say that this is a failure of engineering. Of course, this is how the regulatory epistemology has been so far. Hence, we need to try and figure out how we change the paradigm to agree and understand how do we go about it. I'm conscious of the time, so I'm going to pick up the pace. I want to keep some time for questions. So based on the problem, what I proposed is that I spent some time trying to figure out that how do we resolve this. And what I'm proposing in this paper is a system, a continuous statistical assurance system that is continuous. So the certificate is not something that you receive on one day and then that is true for life. It's something that is live and it's continuous. It's conditional. So it is conditional dependent on what's your operating design domain, as well as how well it is performing within that domain. So there are confidence thresholds and performance criteria that can be pre-agreed, that is monitored live by authorities as well as the operators. Of course, it is not public data, publicly available, but it is something that is available to authorities in a secure portal, such that it is not something where we have to wait for a fatality for someone to see that, oh, this is not performing as it should. As soon as it goes below the threshold of whatever we have agreed, it would flag that this is a problem and an inquiry be set. And it has to be statistical. So it is bounded. It is basically to say that how would it behave in the long tail? How do you basically what happens when it is beyond its confidence zone? What happens then? I'll jump a little bit more into it later on. So the whole loop is entry gate, where you provide your safety case and evidence from simulation as well as a real mile to get the first approval. But then that is one-time activity for approval. Then later on, it's live, where it is a shared monitor that authorities as well as operator has. So you deploy once the approval comes, and then you constantly monitor. And if it performs beyond acceptable limit, you expand or contract your ODD and then go through that again. Certification is an interface. It is basically talking to a system that is a platform, a module that basically shared something that I've been talking. So I'll try to speed up past this. The intention is to create something that is not too complex to deploy, and it is not prohibitive to either side. Something that I touched on, so there should be an agreed confidence threshold that shows that this is effectively where the system is supposed to operate completely level 4 autonomous, where no intervention or restriction is needed. And that confidence mechanism is also studied beforehand at the entry gate. Once it's observed that the confidence drops for whatever reason, deliberation should be kicked in, and that could be through model, where you can have a slightly more capable model that is thinking in a more complex situations rather than acting rapidly as it is needed for real-time operation, as well as you limit the performance. So it is no longer doing all the maneuvers at full capability. It's restricted in the performance to restrict the risk exposure. And once it goes below that threshold, it has to fall back to safe state, whether it's coming to a safe stop or emergency brake, whatever may be appropriate for that scenario. Another aspect that I have covered is how it should calibrate. So calibration, as some of you might know, is a common practice for AVs and most of the other systems that effectively makes the car learn where it is, all the sensors, and based on that, it performs. So that calibration or the sensors have tendency to degrade over time. If the sensors do degrade, the thresholds should change as well. Whether it's sensor, whether it's performing differently for whatever reason in certain ODD, it should reflect in terms of what are the thresholds. The thresholds should not be that, oh, this is what was agreed in San Francisco, hence that is true everywhere. Something that I mentioned a few minutes back about explainability or narration. It's a known problem for all these large models that because internally the way the numbers pass within the large models neural net is not something we can understand or comprehend. It's only the output that we can understand. So a lot of time, what a lot of operators for LLMs or driving models have done is to try and create a chain of thought as an output, but that's a secondary output, that's a secondary head. That is not the actual neural net that's giving you the actuation signals. And that's a big problem. And that also shows that how even the same model, sometimes to simplify in case of LLMs, when you ask that provide your chain of thought, it is only 25% true, let's say in Claude Sonnet 3.7's case, or 39% in DeepSeek's case, or one of the VLA, I think it was AlphaMyo. They have a chain of causation from NVIDIA AlphaMyo. It's only correct in 42% of the case. Hence, it's not really something you can rely on. It's the chances of it being incorrect or it basically doing something different than what it says is more than half. So it's not reliable. Hence, it's important to understand that just by adding a human readable layer will not be a simple solution. We have to think of it cohesively, and there are different techniques to try and actually learn what's going on inside the head. And this is also not true just for automotive. Similar structure for regulation exists for other robotics system as well. Hence, the similar thing apply to wider robotics, even more so if you think how robotaxis as a fleet would probably, let's say in Waymo's case, even with early days, 4,000 cars, they would log hundreds of thousands of miles every day. That is not true for Robo, who perform at a factory. And for them to come to the level of statistical comfort that they can prove by empirical data that this is now statistically safe is going to be years or more than the lifetime of those robots. Hence, it's even more important for rest of the robotics. Hence, I think the system, basically, this whole arrangement asks for few different things. We have to learn to accept the probabilistic proof as the evidence for safety. We have to be comfortable and learn the nuances of it and be comfortable as a community that this is going to be accepted as a legal, safe safety proof so that even insurance can act on it. It has to be mandated. It needs to be where it is clearly stated that these are the bounds that you need to act with, and it is not something where it's dependent on self-certification, because there should be, as I said, a reward for someone who's more diligent. And it has to be something where we agree to fund it for a common platform where the data is aggregated for the wider community. So a new operator which has, let's say, 50 prototype can benefit by the pool of the data and the learning that the whole AV industry had thus far, and also add to it if they have novel methods and stuff like that. So as well as creating that platform where the regulators can see the data live, effectively takes out the burden of bureaucracy that usually is what everyone fears. So that's what I wanted to say, and I'm really sorry that I've almost taken the whole time, but I'll be glad to stay back and answer questions.
Wonderful.
Sorry, Evan.
Thank you, Neil. Yeah, no apology necessary. It was good, a good presentation. I'm just reading your comment with respect to a working group. Yeah, that's something we can take offline and discuss. And there may be possibility. We'll need to gauge interest. I have a quick question for you, and we're a small enough group. If anybody has another question, just follow up, unmute, and ask your question. But I'll start with the first question. Neil, I understand when you have a contained system, you can, and training data, you vet your own training data. Now, I'm not sure in this particular scenario with the continuous statistical approach. I think it makes sense, and you just keep updating and updating, and it's real time. But I'm just curious about validation of the data, so that you're training on good data, and that you can't stray to the common fear with artificial intelligence. What are your thoughts there?
So it's a very good point. So it is important to monitor the input data, but it is, I think, perhaps stepping, going a step beyond what is, in my opinion, what's the word I'm looking for? Encouraging for industry. So ultimately, what we care about is the output, and the verification and validation for that is fairly mature. Taking the holdout data and then proving that this is actually what it's supposed to do, showing that this is your data as ODD, that happens as part of the safety case. So you do show that this is your data, because that's how you would be able to actually demonstrate that your system performs in the ODD that you are suggesting. But you can, like as an operator, everyone goes in much more detail to understand how good the data is, because I think that's in reality bigger challenge than the model, because model effectively, once you set the machine running, it all depends on the kind of data that you provide, besides few parameters. So very good point. When industry comes to a point where there is an appetite for more clarity and involvement, at that point, perhaps we can have more structure, more guideline there. But to start with, I think the output is where it should be sufficient to focus on that.
Okay, good. Anybody else with questions, please feel free to unmute.
And any systems engineering related question as well, I'm happy to answer. I'm not a career systems engineer, but I have done all those activities, writing requirements as well as testing several times for whole systems, and I understand that. So I'm happy to answer. There's a big part of this which is purely systems engineering.
Anything?
Maybe I can go next, Ivan.
Yeah,
so
Simon.
thank you for the presentation. No, that was pretty informative, I would say. Maybe
Thank you.
one question that came to my mind is about the safety assurance thing. Like, based on your experience, is there any guideline or any structured safety case that everybody needs to follow, or it would be solely based on like the person who is putting the safety case together and how they claim the operation of this model or this vehicle is safe? So how does that work actually?
Yeah, so the part that I show, they form the structure. So there is a little more that I explain within the paper. I intentionally kept this presentation a bit brief. But so there are 4 different things that we need to see without dictating the technology. Because we should not be restricting someone from coming with a novel solution which is technically more capable. So being able to show the provable probabilistic safety, which is one part, which is where you are saying that the tail is handled this way. So there is a structure for that. There is ability to show what the system is doing live from these SPIs, as I've called it, safety performance indicators. And the envelope is bounded, where it is not a open one-time pass and forever done scenario. You are constantly monitoring that these are the parameters that we have agreed to monitor, and we will sort of, if it performs for whatever reason, it performs worse. Let's say they had an update with the model, and now those updates somehow behave worse than they were in the past, then the ODD should even shrink. So that's the high-level structure for the safety case. It's intentionally not dictating more in detail in terms of what should be the technology, if that explains.
Yeah, but for example, when they are putting the failure modes together, like different people could come up with different type of failure modes or different type of malfunctions. For example, you simply say provide power. So if I come up with malfunctions, I can list 3, but another person lists 5. And that could result in different FMEA, different failure modes, and then the overall failure would change. So I'm just wondering, would the governance party rely on how you claim your safety case, or they would just set aside a guideline, a standard, and acceptable range for the safety assurance to accept that, yes, this autonomous vehicle is safe to operate?
I understand. So there is a little bit more I discuss within the paper, and it's a bit too long, I understand, from some technical paper standard. What this is proposing is that because this is not a system where you would demonstrate all the cases, all the use cases by empirical evidence, you are demonstrating that by means of simulation, your real world miles, and by your safety case. And when you show simulation and real world miles, when you explain that this is the ODD, this is the operating domain. So if you say that this is going to operate in San Francisco, let's say 24/7, then you have to show in that the diversity of the use case. So the simulation or your real world miles would demonstrate that it operates in winter, in summer, in fall, in morning, in the evening, and on these different streets, because this is what San Francisco has. It has slopes, it has narrow streets, all of those. So your operating domain dictates that, and that is what you would demonstrate to whatever is the regulatory authority in a fashion that is effectively condensed information for that ODD.
Yeah,
It's good point.
One interesting. Oh, go ahead, Amran. Sorry.
Yeah, just a thank you. That's very, very informative session. That's pretty good. Thank you.
You bring up a good point, though, Neil, in terms of the regional applicability. So, what's true in San Francisco may not be true in Calgary or Montreal, and so
or China,
or yeah, it's interesting.
And Japan as well. So because Japan follows different direction, a lot of things are different. Japan also has signs which are not something that a lot of time are in English, or the signs are different, and that's true across the world. Like you go to different places and you would find that, oh, there are differences which don't appear to be huge. To give you an example, something unrelated, I had a shock of my life when I first went to a fuel station in US, because in UK your petrol is green, the nozzle is green, and diesel is black. US is exactly same colors opposite.
Wow. Okay.
So things can be quite interesting, and yes, that's why operating design domain is important. It is always accompanied with the safety case. There's never a safety case which is generally it performs everywhere.
Yes. Oh, very good. Okay, well, we are over time, so I think we better wrap it up here. But I'd like to thank you once again, Neil. This was very informative. I'm certain that we'll have a lot of people looking for the recording, so we'll make those available. As I say, LinkedIn and YouTube, they're available, and at a future date, facing a little bit of a delay with the Nkosi websites, but we'll eventually have access by those means as well. But thank you very much. Thank you, everybody, for joining. Thank you for anybody who's viewing this online after the fact. And with that, take care And
thank you very
we hope
much. Thanks,
yeah.
Evan. Thanks for inviting, and thanks everyone in Cozy for having me. It was great. Good questions as well.
Thank you. Very good. Take care.
Cheers.
Bye
Take
now.
care. Bye-bye.